Welcome to Unit 3, Lesson 4, Types of Energy, the Law of Conservation of Energy Efficiency, and Energy Sources and Energy Conservation. By the end of this lesson, you'll be able to demonstrate an understanding of the types of energy, the law of conservation of energy, efficiency, and energy sources. You know you've been successful when you're able to describe in detail the types of energy, the law of conservation of energy, efficiency, and energy sources. You're able to demonstrate an understanding of how to transfer energy from one form to another and to apply transformations of energy to daily life. So, we have different types of energy. The first is mechanical energy, which is in the form of potential and kinetic. It's energy possessed by an object that are primarily affected by the force of gravity and frictional forces. So an example or an application would be in airplanes. Gravitational energy is a form of potential energy that it's energy possessed by objects that are affected by the force of gravity, and it applies to all objects on Earth and in the universe. Radiant energy is also known as light energy, or electromagnetic radiation. It has potential and kinetic energy. It's energy possessed by oscillating electric and magnetic fields. Continuing with types of energy, we have electrical energy, known as static electricity. It's a potential energy. Energy possessed by accumulated static charges. Electrical energy in terms of current electricity, so it has potential and kinetic. It's energy possessed by flowing charges, and we'll learn more about this in future units. Thermal energy is sometimes incorrectly called heat energy. It is potential and kinetic energy, and it's energy possessed by randomly moving atoms and molecules, which we will learn about shortly. Sound energy is potential and kinetic. It's energy possessed by large groups of oscillating atoms and molecules. Continuing on, we have nuclear energy, also known as atomic energy. It is a form of potential energy, and it's energy possessed by protons and neutrons in atomic nuclei, and we will learn more about this in the future. Elastic energy, also known as spring energy, is a form of potential energy. It's energy possessed by materials that are stretched, compressed, or twisted and tend to return to their original shape. Chemical energy, also known as bond energy, fuel energy, food energy, molecular energy, and internal energy, are all forms of a potential energy, and it's energy associated with bonds in various molecules. So, an energy transformation is the change of one type of energy into another. So, for example, changing a potential energy into kinetic energy. So, in this example at the top here, the girl holding the ball contains potential energy, and then once it is dropped, that potential energy is transformed into kinetic energy. So more examples of energy transformations. In a light bulb, transforms the electrical energy into radiant energy or light energy and thermal energy in the form of heat. In a car engine, a gasoline engine transforms the chemical energy in gasoline into kinetic energy, thermal energy, and sound energy. And then we have an electrical power station. So we have some form of coal, and it is turned into electricity or electrical energy, which is then taken up by a meter. You have an energy electricity meter at your house. We talked about how it's measured in kilowatt hours, and that electrical energy is transformed into the heat energy of a kettle, which eventually leads to a hot drink. So, the law of conservation of energy states that energy is neither created nor destroyed when energy is transformed from one form or another, no energy is lost. So ultimately, we can't lose any energy along the way. It can be converted into a form that we don't necessarily want. So for example, when we were talking about the car engine, we would hope that all of the potential energy in the gasoline is converted into momentum and kinetic energy to move the car forward, but we do lose some of the energy to heat and to sound. So we haven't actually lost any of the energy. We've lost the potential of the energy, and because it has been transformed into a form that we might not necessarily want or need. So furthermore, a light bulb may transform 100 joules of electrical energy into 5 joules of radiant energy and 95 joules of thermal energy, which means that we get a portion of that 100 joules of electrical energy in the form of light and the rest in the form of heat. And we know this, when we touch a light bulb, it's hot to the touch. But it's important to note that the total amount of energy in that process has not changed. It's still 100 joules of energy. So that electrical energy has been converted into both thermal and radiant, but at the end of the day, it is still 100 joules of energy. So we can analyze a dive made by a diver in terms of the diver's potential energy, gravitational energy, kinetic energy, and total mechanical energy, which is the sum of, remember, we talked about this in the previous lesson, the sum of the gravitational energy and the kinetic energy. So at the top of the dive, before the diver actually moves off the platform, then you can see that their potential energy at the top of the dive would be 6.4 kilojoules, and they have 0 kinetic energy because they have not moved yet. And then the total mechanical energy would be the two of them added together. And so once the diver has started the dive, the potential energy will transform into kinetic energy. So we can see here that at the halfway point, half of the potential energy has been converted into kinetic energy, but the total amount of mechanical energy has not changed. Once the diver hits the water's surface, so the dive is over, the potential energy has been fully converted into kinetic energy, but again, the total mechanical energy has not changed. So within that system, the mechanical energy is the same as it was at the start. It's just in a different form. So we can think of this in terms of the algebraic and mathematical formula as well. So we can think of this as the gravitational potential energy, which we saw in a previous lesson was mass times acceleration due to gravity times height, plus the kinetic energy, which was 1/2 mass times velocity squared. And it has to equal some value that stays the same. So no matter what we do throughout the system, throughout the event taking place, the transformation, the gravitational potential energy and the kinetic energy have to stay the same. Okay? And ultimately that means that energy is conserved. So this is an example. If we are looking at this free fall of this ball from the top of an apartment building, then we can see that its potential energy and its kinetic energy are going to keep a total sum of the amount of energy it would take for the ball to fall, and we are able to calculate this throughout using the height and the velocity and the time. So we are able to see that if we start out with a potential energy of 800 joules, then we have no kinetic energy. So remember that this is potential energy and this is kinetic. energy. And the two of them together have to keep the same total mechanical energy. So this is mechanical energy. So all the way through, you can see, just as we did with the diver, that as the potential energy is converted into kinetic energy, the sum stays the same, but the type of energy, the form of energy, is what is changing. So many problems that we've been solving with kinematics can be solved using energy methods. For many problems, energy methods are easier, and for some it is the only possible way to solve them. So let's do one both ways. So if we have a 185 kilogram orangutan drops from a 7-meter high branch in a rainforest in Indonesia. So how fast is he moving when he hits the ground? So we know that we have a mass of 185 kilograms. We know that we have a height of 7 meters. We know that we have an acceleration of 9.8 meters per second squared. And then we can, and if he's resting at the top, then we know that we have an initial velocity of 0 meters per second. So we can fill this in, and we see that we just fill the numbers in for the values that we have. In this case, the delta x is h, so we can think of it as delta x as well, or h. And remember that he's dropping, so it's going to be a negative. Okay, so we're just going to fill the values in for v and a and delta x or h, and that on the kinematics gets us 11.71 meters per second. Now for the second one, our conservation of energy is our initial energy has to be the same as our final energy, so our potential energy has to be the same as our kinetic energy. So we also know that A can be thought of as G, as the acceleration due to gravity. So we know that we have a mass and our acceleration due to gravity, followed by our height, which we don't need to worry about direction because we are not worrying about, it's just velocity, it doesn't have a direction. So we fill those in and we get 11.71 meters per second. And it's important to note that in both equations, the mass is not important. It is not even in the equation for kinematics, and for the conservation of energy, it's on both sides, so it can cancel out. So we can rewrite this equation and move the 1/2 over, which gets us 2 times the acceleration due to gravity times the height, which just equals velocity squared, and it's a way to isolate velocity on its own, and then we would take the square root of both sides to get velocity by itself. So the term efficiency is the amount of useful energy produced in an energy transformation expressed as a percentage of the total amount of energy used. So we talked about this light bulb situation before, and there's an amount of energy that is useful, that is what we want it to do, for example, show light, and then there's an amount of energy that is kind of a byproduct. It's happening, but it's not necessarily what we want. So in the case of a light bulb, that could be heat. In the case of an engine, that could be heat and sound. So efficiency is the ratio of the amount of useful energy produced, so energy output, to the amount of energy used. And it's always expressed as a percentage. Okay, so for example, the incandescent light bulbs transform a very small percentage of the electrical energy supplied into radiant energy, light energy. Therefore, incandescent bulbs produce a lot of thermal energy waste. So it's energy, but it's not in a form that we particularly need. So incandescent light bulbs are 5% efficient at converting electrical energy, the supplied energy, into radiant energy, which is the desired energy. Okay. And this is the end of our lesson, so be sure to complete the quiz below the lesson, and if you have any questions, please contact your teacher.